Okay, Unit 3, Electron Configurations and Orbital Diagrams. So let's take a look here. There's this nice diagram here on this first slide showing you these labeled boxes and these different energies. So hopefully by the end of today's lesson, you will have a good idea what this diagram is representing. So today we're going to be able to write electron configurations of elements and ions using the off-bow principle. We're going to be able to also fill in orbital diagrams of atoms and ions and elements using off-bow principle, Hund's rule, and Pauli exclusion principle. Now recall from the last lesson on the quantum mechanical model that Schrodinger did his wave equations, his wave functions, and he was able to graph and determine the shapes of the orbitals where the electrons are going to be likely to be 90% of the time. So that's statistical model. So realize when we're placing things in electron configurations and orbital diagrams, we are placing them where we think they are going to be 90% of the time, where they are likely to be. Now the orbitals here are pictured on this slide, where you can see like the s orbital and the p orbitals and the d orbitals. There's 5 orbitals for d, there's 7 orbitals for f, 3 orbitals for p, and there's only the 1 type of orbital for s. And s, p, d, and f are sublevels. So within each sublevel, you have your particular orbitals that you can have. So in a p sublevel, here you have 3 possible orbitals where electrons can fill. In a d sublevel, you have 5 different d orbitals where electrons can occupy and so forth. So when we're going to be looking at these diagrams and things, obviously we're not going to draw these funky shapes and place electrons in these funky shapes. So instead, we're going to use a more concrete model to represent our orbitals. Because the spherical and dumbbell shapes are okay and probably easy to work with, but you get into the D's and F's and it gets way too complicated. So instead of trying to actually use the actual shapes the way they look, we are going to represent them with boxes or lines and represent the orbitals that way. Before we get to that, though, let's talk some electron configuration lingo. The arrangement of electrons in an atom is known as its electron configuration. Electrons in atoms tend to assume arrangements that have the lowest possible energies for the orbitals. Now, what you have to consider about chemistry, and this is the way it goes for most chemistry concepts, and the atoms and the molecules and everything are looking for the lowest energy possible state. It's more stable at a lower energy than as something that would be at a high energy. So it's the stability, the lower energy state is what we're looking for. And that applies here to electron configurations because the electrons are going to arrange themselves to being in the lowest possible energy, potential energy possible. Now we call this lowest possible arrangement the ground state configuration. And you knew that in the previous one where we were at the ground state. Then you either heated it with the flame or you gave it electricity in the gas tube. Then the electrons become excited and they jump to outside, farther out, higher energy levels. That would be the excited state. But here in this particular set of notes, we're going to be arranging the electrons in their ground state configuration, how they're going to look at their lowest energy level state. The normal state is what we would say. There are 3 rules, general rules for filling orbitals and creating these electron configurations. One's called the off-bow principle, the second one's called the Pauli exclusion principle, and Hund's rule. Now, give them analogies, because this is very abstract. We call the off-bow principle the lazy tenant rule. The Pauli exclusion principle is the opposite spin rule, and Hund's rule would be the empty bus seat kind of idea here. And I'll explain what those analogies are in just a minute. 2 of them are named for people. Pauli and Hund are actually named after people who discovered and theorized and created these principles and these rules. Off-bow, though, is just a German word for build up. So off-bow is not actually a particular person, but that's what the name for why that name came about. It's German for building up. And you're going to understand what building up means in just a second. So this is an off-bow diagram. And those orbitals I showed you with the spherical, the dumbbell, and the D's and the F's that look like the funny balloons and the donuts, we are not going to draw them. Instead, we're going to represent them with the boxes. So this 1s is representing a spherical shaped orbital. The 2s is also a spherical shaped orbital. It's just a little bit farther out. It's in the second energy level instead of the first energy level. So we're getting a little bit farther away from the nucleus. The 2p here. The 2p is a sublevel because it has 3 orbitals in it. You have 3 boxes, 1, 2, 3. So each box is representing one of those dumbbell-shaped orbitals that we saw on the previous slide. You get up here into the Ds. The 3D sublevel doesn't start till principal energy level 3, so we get a little bit farther out from the nucleus. But these are those 5 orbitals, those 5 shapes that we saw on the previous slide. Each box is representing one of those shapes. And then if you look at the 4F here, each box is representing one of those shapes that was in the bottom row with the green, with all the funny balloon things. Each box is representing one of those shapes. And we're placing electrons in there. That's what we're doing. This is our analogy. We're using these boxes in order to fill our electrons. Now the off-bell principle means you're starting at the bottom and you're working your way up because the lowest energy, 1s, is the one that's closest to the nucleus, so it has the lowest potential energy of all of the orbitals. So the first orbital that's always going to fill is going to be the 1s. The second orbital to fill is going to be the 2s. The third orbital to fill is going to be the 2p, and then 3s, 3p. Now this is where it gets interesting because the 4s, if you look at this diagram, is slightly lower than the 3d, so it gets a little bit out of order. Just there, the 4s, 3d, 4p, and so forth. And there's a system here. Now you can memorize this in order if you want to, but that's a lot of work and not necessary. What I'm going to show you later on is how to do it using the periodic table, because the periodic table establishes the pattern for you. So you don't have to memorize this particular order. You just have to know where each block is, and then you follow the rules and you can use the periodic table to determine where electrons are going to go. So start at the bottom, work your way up, 1s, then 2s, then 2p, 3s, and so forth. That's what we're going to do when we follow the off-bell principle. Lowest energy level fills first, then you move on to the next one, and so forth. We call it the lazy tenant rule because imagine you live, say, in an apartment building, or it's an office building that has 5 stories. We're going with the idea that there is no elevator available. So you would actually have to walk upstairs to get to the other levels. So in this particular case, if you're an individual who doesn't want to expend a lot of energy, probably likely would like to be on the bottom floor or the first floor, like the 1s is. The 1s would be like the first floor, whereas like the 5s would be like the 5th floor, which would require lots of stairs to get up there. So obviously you could see that's an increase in the energy. So that's where we kind of get that analogy of the lazy tenant rule. If you're living in an apartment building and you don't have elevators and you have to walk up all these stairs, that's the same idea, where you'd rather be on the bottom floor because you wouldn't then have to climb any stairs. The Pauli exclusion principle is a little bit challenging to talk about when we're not really going to go into the detail of what quantum numbers are. And it basically says that no 2 electrons have the same set of 4 quantum numbers. And we're not going to go in and describe all the quantum numbers, but the quantum number system is really just giving the electron an address. It's basically saying we predict it's going to be here at this location. If you know all the quantum numbers, what you figure out eventually is 2 things come from this idea, that only 2 electrons can occupy an orbital, period. The other thing is that when they occupy the same orbital, those 2 electrons, they have to spin in opposite directions. So that by doing that, by only having 2 electrons and having them spin in opposite direction, that ensures that there are no 2 electrons that have exactly the same 4 quantum numbers. When I say spin too, like we represent the spin, an up arrow and a down arrow. Well, it's not like spinning up and spinning down. It's actually spinning clockwise and counterclockwise. So the up arrow is indicating the clockwise spin, whereas the down arrow is indicating the counterclockwise spin. And you might say, hey, why are they spinning in opposite directions? Well, they're occupying the same orbital, and electrons have a tendency to repel other electrons because they are negatively charged. So therefore, obviously, giving them a little bit more space if they're spinning in the opposite direction. Hund's rule. Hund's rule states that when you have orbitals of equal energy on the same sublevel, like the P, D, and F, how we had those boxes in a row, where there were 3 boxes for the P, 5 boxes for the D, and 7 boxes for the F. Those are equal energy orbitals because they all are in the same energy part of the diagram. If you have those particular orbitals, you must fill the orbitals individually first before pairing them up. So if we're looking here at our example between the one over here to the left and the one over here to the right, the one on the left would be incorrect because you put 2 in each. Well, according to Hund's rule, we want to put 1 in each first and then pair them up. That kind of follows this idea of the empty bus seat. Now, if you're on a bus that only has like 2 or 3, maybe 4 other people, there's lots of space and you don't know any of them, say you're just by yourself, you're not typically going to see somebody go sit right next to a person they don't know. Usually you'd go to a space where there's hardly anybody sitting there, so you would just sit down and space out. Now, this picture is one of looking at how they're blocking off seats for COVID, so it's kind of like we're doing that anyways due to the pandemic, but under non-pandemic situations, you just, if their bus is pretty empty, you don't typically just rush out to sit right next to somebody you don't know. Same idea here, the electrons would rather be spaced out in separate orbitals of the same level than to be pairing up if they don't have to. Once again, back to the idea that electrons are negatively charged particles and have a tendency to repel one another. So if they have another orbital space they can go to rather than pairing up, that is what the tendency is going to be that they're going to do. Now, looking at general rules for filling these orbitals for the example of this 2p sublevel. This 2p sublevel has 3 orbitals, the px, the py, the pz on here. So all those dumbbell shapes going different directions. But if I add 1 electron, I would put 1 in the first box, spinning in the clockwise direction. If I'm going to fill 2 electrons, if I needed to fill a second electron in this 2p, I would put 1 in the first box, 1 in the second box, both spinning clockwise or pointing up, the arrow pointing up. And the arrows mean that the arrows are actually representing our electrons, by the way, if you haven't already figured that out. So when we put an arrow in the box, that is actually representing the electron. We add a third electron to the boxes here. This is how it would look. 1, 2, 3, all pointing up. They're all spinning clockwise here. Now, if we have to add a 4th electron, this is what you're going to see. That is when you start pairing them up and they spin in the opposite direction. So now we've got to make sure that we're spinning them correctly for Pauli exclusion principle and that we're only putting 2 electrons in that particular box. If we had to add a 5th electron to a P sublevel, then of course there would be 2 paired up, the first 2 boxes, and then the last one is unpaired. And then if we had to completely fill the 2p, then all of them are paired up, one spinning up, one spinning, one spinning clockwise, one spinning counterclockwise in each orbital. And that's how you would fill them for the P sublevel. Now this also applies to the D and the Fs because they have equal energy orbitals. You would put 1 in each first before you pair them up. So we're going to go ahead and practice filling these orbital diagrams for nitrogen, magnesium, and silicon. And we're going to use off-Bowl principle, we're going to use Pauli exclusion principle, and we're going to use Hund's rule here in order to do that. Before I can just start filling in the boxes though, what do I need to know about each element? What is the main thing that I need to know? We have nitrogen, magnesium, and silicon here. And I'm placing their electrons into their respective orbitals. What must I know first, though, before I can begin? The number of electrons. Good. How do I figure that out? Very good, very good. How do you figure out the number of electrons again? Anybody remember? Yes, we need the atomic number. So we need to pull out our handy dandy periodic table to figure that out. So we're looking here at nitrogen, magnesium, and silicon. These were the three elements. What do we know about an atom of nitrogen in terms of its electrons? The atomic number is the proton number, but if it's just an atom, that means it's neutral. So that means the electrons have to be the same number. So in this case, nitrogen has 7 electrons. How many is silicon going to have? 14 electrons. Good. 14 electrons here. And then how many for magnesium? 12. So now that we know how many that we need to fill, we can go back to our diagram and start filling them. Now let's start with the first rule, off-bow principle. Off-bow principle says build up, start with the lowest energy level first. So which one am I always going to fill first before I move on? The 1s, good. So I'm going to start filling. Here's nitrogen. I have 7 electrons to work with. I'm going to put 2 here in the first box, like so. Now I'm down to 5. Add another 2. I'm going to fill the 2s completely. So now I have 3 left. Now we have to fill the 2p and follow Hund's rule. So we put 1 in each first. Okay, like so. That's a total of 7 electrons. So I have completed the orbital diagram here for nitrogen. Now magnesium, we said, had 12 electrons, so we're going to fill it just the same way. So go ahead and take a moment to fill in magnesium and silicon. I'm going to give you a minute to do that. Okay, getting ready here to fill. So 12 electrons, I'm just going to keep building up. So here nitrogen filled in 7. So I'm going to keep going from the 7. I know how those first 7 fill, so I put 2 here. Put 2 here. That's 4 of my 12. I have 8 more. 1, 2, 3, 4, 5, 6. That's 10 total. Now I always fill it that way. I always put 1 in each first before I pair them up, even though I know that it's going to completely fill. So I have 10 filled. I need to add 2 more. So the 3s is filled for magnesium. Silicon has 14 electrons and we need to fill that. So obviously silicon is going to look very similar to magnesium. Those first 12 are going to fill just like magnesium did, and then we just have to add in the other 2. So 1, 2 go in the 1s, the lowest energy level. We're spinning them in opposite direction and only putting 2 in there because of Pauli's rule, Pauli exclusion principle. Then Hund's rule, 1 in each first before we pair them up, like so. And then we fill the 3s because that's the next lowest energy level. Now that's 12, it matches magnesium, and then I can fill in the last 2. Hund's rule, I'm separating them and putting 1 in the first 2 boxes of the 3p sublevel. Now, just to add on here real quick, the 3, the 4, the 2, the 1, these are those principal energy levels. And in the Bohr model, they looked like the rings around the nucleus. Now, we know that they're not that simple ring shape. However, those principal energy levels do exist. Within them, though, are multiple shapes, the spherical, the dumbbell, and then as you get farther out, you add in the D, and then once you get to principal energy level 4, you can see the F. Those F-shaped orbitals start to appear. So once again, you could check your answers. I do have all of them written in here, so if you don't get a chance to look back or want to go back to the answers, they will all be in this PowerPoint. Now I wanted to show you real quickly too that orbital diagrams don't always look exactly the same. You can use boxes or lines. So in the previous one, we were using boxes. And here they kind of do even the half arrow effect where they do one half arrow up and one half arrow down. They don't always look the same. So if you're researching or looking around. Sometimes the orbital diagrams have slight little nuances to them. They can, be across. They can go across rather than being stacked. Like this one is more stacked like the one in the previous slide, where they went by energy. Sometimes they just draw them, across. Like here, fluorine, drawing fluorine across here, and then using like the half arrow effect. So the arrows, of course, remember, are the electrons, but you can write them either way. It really doesn't matter to me. Another comparison, the stacked versus going in a straight line. The stacked is more like the off-bow diagram, where it's showing you the energy of each orbital as you're increasingly going up. And you could also write them like this, like where you just write them and use lines. You just have to make sure you label everything. You don't have to necessarily use boxes. Say I wanted to do a 3D, well, it could be 1, 2, 3, 4, 5 lines instead of using the box model here. It really doesn't matter, but you might see them represented in all of these different fashions. So I wanted you to, have exposure to that and go like, what is that? Okay, yeah, no, that's actually still another way of representing an orbital diagram. You can use lines, you can use boxes, you can use half arrows, you can use full arrows. Just make sure that you label your principal energy level and your sublevel, which would be like 3D. The principal energy level is the 3, the D is the sublevel, and then there's 5 lines in it representing all 5 orbitals in that particular sublevel. And each orbital can handle or hold a maximum of 2 electrons according to Pauli exclusion principle. So if you look here, the first S's, they can hold a maximum of 2 electrons. P's can hold a maximum of 6 electrons. D's can hold a maximum of 10 electrons, and F's can hold a maximum of 14 electrons, because each box can hold up to 2. Now we're going to go ahead and look at oxygen, and we're going to draw our own orbital diagram. And I went ahead and looked at the periodic table for you. So we know that oxygen has 8 electrons. And we're going to, create our own orbital diagram, drawing that in. So if I'm starting it with the off-bow principle, what's going to be my first energy level that I need to draw? I have, yes, 8 electrons to fill, so I need to draw the 1s, and I like to do the lines because the boxes just take more time. So I'm going to do 1s, and I'm going to fill it with 2 electrons. You could do the half arrows like that. So you get 2, or now I'm down to 6 electrons, 6 left. What's the next orbital to fill according to off-bow principle? Next is the 2s, good. So we go up, we go down. Now I have 4 more to go. After the 2s comes the 2p. So here I have 4 electrons to fill in there. So I'm going to put 1, oops. If I'm going to do half arrows, I need to stick with half arrows. So here we go. 1, 2, 3, 4. So you only pair up the last one in there. And so this would be the orbital diagram for oxygen. Now we're going to look at how to do the notation for the electron configuration. And it is kind of based off of what we see here in our orbital diagram. I can definitely use that. The way the electron configuration works is you start with the principal energy level, the sublevel, and then how many electrons are in there. Well, there's 2 electrons in the 1s, so then I make it a superscript of 2 representing those 2 electrons that are in that particular orbital. Next, I have my 2s, so this would be 2s2. The principal energy level, the sublevel, and then the number of electrons is the superscript. In the 2p, this particular one, 1, 2, 3, 4, so I have 4 electrons, my superscript is going to be a 4. So the electron configuration notation is 1s2, 2s2, 2p4, and that's how you would write it out. A lot of people get orbital diagram confused with electron configuration, but orbital diagram are the arrows and the boxes or the lines. electron configuration is always the 1s2 with the superscript, 2s2 superscript, and so forth. So this is what you would see if we were doing the orbital diagram for oxygen and the electron configuration for oxygen. Oops. Why are you up? Come on, go away. Thank you. Just wanted to erase. Let me erase real quick. There we go. Because it's a nice, beautiful, colorful one here. The 1s, here's the box and the full arrow approach. And then the 2p, 1, 2, 3, 4. And then the electron configuration fills in accordingly. So that's how you would write out the orbital diagram, electron configuration, or you could do it my way where I did the lines and the half arrows. Either way would be accepted. Now your turn. You're going to try to fill in the orbital diagram for iron. 26 electrons. I already looked at the periodic table for you, figured that one out. So go ahead and take a moment to fill in the arrows and do the electron configuration for iron. Your turn, practice. All right, starting with off-bow principle and the lowest energy level possible. I'm going to do my arrows. That's 2 of my 26. So kind of keep a mental tally. 3, 4, 5, 6, 7, 8, 9, 10. Still have 16 to go. You can kind of keep track that way. 3s comes next, so that's 12. 13, 14, 15, 16, 17, 18. So I've used 18 of my 26. That means I have 8 more to go. Now this is where it gets a little strange because it seems out of order, but the 4s right here is slightly lower in energy than the 3d, which is just like slightly above it. So the 4s does fill before the 3d. Based off of the shape of the orbital being spherical, some reason does allow for more penetrating effects, so it reduces the potential energy just slightly. So we would want to put 2 here of the 8. Now I'm down to 6. So I'm filling my 3D using Hund's rule. I put 1 in each box first with the 6, so that's 5 of my 6, and then the 1 pairs up right there. So this is the orbital diagram for iron, or this is an orbital diagram for iron. Now I can use this to write out my configuration because in my 1s, I have 2 electrons. In my 2s, I have 2 electrons. The 2p has 6 electrons. The 3s has 2. The 3p fills up completely with 6. And then comes the 4s, that's a 2, and then the 3d has only 1, 2, 3, 4, 5, 6 in it. So that would be the electron configuration for iron. And as stated before, the answer is in here, so you can go back and refer to it if necessary, or go back and rework the problem if necessary. So you can take a look at that. Now talking about helpful patterns on the periodic table. So drawing out the orbital diagram for iron and figuring out the configuration from the orbital diagram seems like a very tedious, time-consuming process. Well, it doesn't have to be that time-consuming in order to do an electron configuration, because the periodic table has the pattern there for you. And this is why you wouldn't have to memorize the off-bow diagram or the stacked one that you've seen in the previous slides. The first 2 columns are called the S block, and they apply to their number of the rows. And the row number is N, which is our principal energy levels. Principal energy levels N. So N equals 1, that's the first row. That's the one that's closest to the nucleus. And if you're thinking about the Bohr model, that's like the first ring outside the nucleus. We know it's not a ring really, it's going to be a spherical shaped orbital, but you know, just giving you kind of more of a concrete example to imagine. The second one over here is the P. I guess I should comment on this other 1s element. This is helium, and helium is a 1s element because technically it could go right here above the alkaline earth metals. Helium has 2 valence electrons, just like the rest of the alkaline earth metals. The reason why it's not positioned over there like hydrogen's positioned above the alkali metals is because helium's chemical and physical properties behave more like noble gases. So they put it in the noble gas particular column because it behaves more like a noble gas, although technically because it has 2 valence electrons, it could go over there in this slot, this particular area right here. So it is considered part of the S block, and it's part of that 1s row. The P block over here are the rest of the tall columns. So, you know, boron through neon over here, that's going to be your 2P. This is aluminum through argon and so forth. The 2P row, the 3P row. The 2s row, the 3s over here in this block. Now this is where it gets a little strange because there's always exceptions in chemistry, is the D block, which are the transition metals right here. That's what we would label the D block. They are 1 row behind the actual periods over here. So like we do n-1. So this particular row is 4, but this starts at 3D. So it's like 4 minus 1. So that's why it's 3D here. But it goes 4s, 3d. But if you think about what we just filled in iron, didn't the 4s fill before the 3d based off of the energy? Yes, it did. So it is kind of nice that it goes in that sequence for us because it's putting it in the correct lowest energy orbital first. The 4s comes before the 3d because it is slightly lower in energy. The last one down here is the F block, which we're not really going to do much with. I mean, I might give you one of these as a bonus because, you know, it's just a little trickier, but if you'd like to learn and do the F block elements, that's fine. I did throw in a couple to see who wants to take on the challenge. But remember, these 2 rows actually insert right here. They insert there. So it spreads out the table to make it extra wide. So really, this is the 6th row and the 7th row. The F sublevels start 2 numbers behind their actual row. So that's why it's n-2. So this is the 6th row minus 2. That's why this is labeled 4F. And if you want to follow the pattern of the way it would fill, you would fill the 6S, then you would go down here and fill the 4F, and then go into the 5D. So you have to remember that you have to insert them right here if you're filling electrons in those particular energy levels. And then, of course, the 7th row, that is where the 5F would come in. And it would insert right here at this point between the 7S and the 6D. This one I believe, put in your notes here that kind of sums it all up here, but don't forget, right here, this is where the insert occurs of those 2 rows. So 6S fills, then 4F, then 5D. 7S fills, then 5F, then 6D. Yes, they always go up there on the YouTube playlist. Now, what we're going to do here is use the pattern of the periodic table to help us speed up writing out electron configurations. What you need to know about the period number. The period number is designated N, or the principal energy level. And they match for S and P. S and P match the N number exactly. Remember, D is n-1 and F is n-2, okay? In order to match to the correct sublevel. The S and P blocks are going to represent our total valence electrons. Now, the valence electrons, we already kind of went over, go with the columns, like column 1 has 1, column 2 has 2 valence electrons, like the halogens in group 17 have 7, and so forth. We're going to be able to show you why that is after this, but it's basically the S and P block, the outer energy levels. If you add them together, that's going to total and give you the number of valence electrons in the particular atom. Now the column within the sublevel block is going to indicate the number of electrons. So let's take a look at what we're talking about here. What does this all mean? This is a really good one because it's already labeled for you. So here is our S block right here. And so this is the 1s, this is the 2s, this is the 3s, and so forth. The first column, the superscript would be a 1 because it would be 1 electron in that s. The second column is a subscript or a superscript of 2 because there'd be 2 electrons added at that point. Don't forget helium kind of belongs here because it is part of the 1s configuration. If you're looking here at the D block shell, okay, the D blocks, this is like D1, D2, D3, 3 electrons in the D for vanadium and niobium and some of these other elements for that particular column. Over here, the P block, P1s, P2s, P3, P4, P5, P6. You're adding your electrons per block on the periodic table, per square on the periodic table. You're adding an electron for each square, basically. Now down here in the F block, like I said, we're probably not going to do much with it, but remember it inserts here. Lanthanum starts the F block, but this is where it gets interesting. The F block gets confusing because LU and LR are considered the first one in the D. So that would be D1. That means HF and RF, these guys are D2s, D3, D4, D5, and so forth. So we are going to follow this pattern on the periodic table, like this is 2p, 3p, 4p, 5p, and we're going to add our electrons just by going through the periodic table, following these patterns. Hydrogen is the most simplistic electron configuration because hydrogen only has 1 electron. But let's go ahead and look at hydrogen's notation so that we understand what we're actually writing down here from the pattern on the periodic table. So hydrogen's going to be 1s1. Only 1 electron, it's going to put that electron in the 1s because it's the lowest energy level possible. We know this. So where are we getting this from? The 1 is the period right here. The S is the S block right here, S block. And this one, of course, is from being in the first column of the S block. So I know how to fill that completely. Let's try one that isn't as simple as hydrogen, just to get the notation down a little bit better. Let's do palladium, PD, which happens to be right here. It's right smack dab in the middle of the transition metals in the D block. So this one's going to take a little while to work our way down to PD on the periodic table. So I'm just going to follow the patterns. This is the 1s, 2s, 3s, 4s, 5s, 6s, 7s, and so forth. Over here's the 2p, 3p, here's the 4p, 5p, 6p, whatever, okay? We're not going to get down here to the F's because the F's don't start till here, so we don't have to really concern ourselves with how that pattern is going to go. But what I'm going to do is I'm just going to start filling my electrons. Each square is representing an electron that I'm filling, and I'm going to go ahead and switch colors to make it a little bit easier to see. So let's go with purple here. All right, so I'm going to fill here. I'm going to fill my 1s's. So my first part of the configuration is 1s, and I'm going to keep working down. Here's my 2s's. That's 1 electron filled, 2s2. I'm going to fill my 2p's, 1, 2, 3, 4, 5, 6. 6 electrons for each block on the table. Then I'm going to fill my 3s's. I'm just going to keep going left to right till I get to my official element. This is the 3s. 3p, going through the 3p, so 3p6. 4s, I'm filling that completely. 4s2. Up here's, remember this one starts at the 3d because it's 1 row behind. So now scandium all the way to zinc down here. That is the 3d section. I'm going to completely fill it, 10 electrons in that section. So 3d10. 1, 2, 3, 4, 5, 6 in my 4p over here. Then I do the 5s, that's the next row. 5s2 comes in, fills, and now I'm almost to palladium. So now I count 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I go 8 electrons into the 4d, so 4d8, and that is the complete electron configuration for palladium. If I wanted to do another element, I would just start right back at the top of the table and I'd start filling, going through the pattern on the periodic table. So let's take a look. Just like I was doing on the periodic table, I just keep filling them as I go. All the way through the 5s there. Now I'm finally getting into that 4d and I finally get to my element and I end up with my entire electron configuration for PD. So what you need to do right now is go ahead and get out your periodic table, which I have here in the PowerPoint. I can just leave this one up for you to work off of. But I want you to do fluorine, silicon, manganese, bromine, and tungsten. Now tungsten's the challenging one because if you notice down here, tungsten is past the F block. So you have to go into the F block. Don't forget that these guys right here, this starts the D1s, okay? Actually, this is going to be 5D1, and this would be 6D1. But yes, if you want to, work off of tungsten, you have to go into the F block and then come out here and be in the 5D to get to tungsten. So go ahead and take, 3 or 4 minutes. I want you to write out the configurations using the periodic table for those 5 elements. Okay, so let's take a look here and work through some of these together, and you can check yourself and see how you did. So let's start with fluorine here at the top. Here's fluorine. I'm just going to work my way down to fluorine, so I'm going to go through the 1s, which is hydrogen and helium. So here's my configuration, 1s2, lithium and beryllium, those are the 2s elements. I'm going to add electrons through them. And then 1, 2, 3, 4, 5. This is the 2p, so that's going to be 2p5. Fluorine's a nice short electron configuration. It only has 9 electrons to begin with, so that's pretty helpful. Let's look at the next one. I'm going to do it in a different color though, so it can contrast. So let's start with green. All right, silicon. Let's do silicon. Starting again at the top, working my way down for silicon. I'm going to do silicon's configuration. So I'm going to go through the 1s, the 2s, completely fill that, go over here, completely fill the 2p. Each block counts as an electron. So here, this is the 3s. I'm going to fill that as well, 3s2. Now when I'm going to start, here's the 3p. I'm going to go 1, 2 into the 3p, so 3p2. So silicon ends on 3p2, and that would be its configuration. Let's go for a larger element, like manganese. Let's take a look at manganese. Not to confuse it with magnesium, because lots of people do, but manganese is right here. It's a transition metal. So for manganese, here I go, starting back at the top of the table. Obviously, I'm going to completely do the same thing I did up till silicon here. So we're going to have 1s2 fill, 2s2, 2p6, that's boron through neon, sodium magnesium, that's 3s2, then aluminum through argon, that's the 3p, and all 6 of them fill, and then here K, potassium and calcium, this is the 4s, or this is the 4th row of the S block. So this becomes 4s2, we fill that completely. Now we're into the 3D. The 3D component, 1, 2, 3, 4, 5. 5 into the 3D, so 3D5. That would be the end of the manganese configuration. So this was manganese, red and manganese. Let's look at a different color for bromine. Bromine is a little bit longer than manganese. Let's try blue here. Bromine's over here. It's a halogen. You found that. So it's basically going to go same thing as manganese, but we're just going to keep adding on. We're going to go completely through the 3D, and then we'll end up over here in this row, which happens to be the 4p. So bromine here, we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That puts me right here. I'm already in the 4s. Now I'm going to go through the 3D completely. 3d10, and then 1, 2, 3, 4, 5. So 4p5. Woo, that one, as you can see, they get longer as you go down the table because you're adding in way more electrons. Now tungsten, oh, that's a fun one. For those that care and want to know how to do the F block, let's go ahead and do the F block. Oh, maybe I should choose a different color. Here, let's go with the dark blue. Dark blue for tungsten. All right, so I'm going to write it down here, though, across as we go. So once again, starting at the top, working our way down, we're going to go through the 1s. 1s2, lithium, beryllium, 2s2. Boron through neon, 2p6. Sodium and magnesium, 3s2. Aluminum through argons, that's the 3p row, 3p6. Potassium, calcium, that's 4s2. Scandium through zinc, it represents the 3d10. Gallium through krypton is 4p6. Rubidium, strontium here, this is the 5s. We're filling the 5s. Now we're going to go completely through the 4d. 4d10, and then indium through xenon all the way over here. That's going to be your 5p6. So far normal as we're going. Now we fill the 6s. Cesium, barium is the 6s, so we're going to fill 6s. This is where you would go the other direction, because now from here you got to go into the F block. This is the 4f. 4f block, and we're going to completely fill the 4f block. So it's going to be 4f14. There's 14 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 blocks in that F. This one starts the 5D, so 5D comes next. So we have 1 in the 5D, 2 in the 5D, 3 in the 5D, and 4 in the 5D, so we end up at 5D4. Tungsten is quite a long configuration. That's why it would be bonus. You don't have to do ones in the F block, so I would only provide that as a bonus question. But if you were interested and wanted to see one worked out, there you have it. Once again, the answers are here. If you need to go back and refer to them in the PowerPoint, you can pull them up, pull up the Google Slides, or download the PowerPoint. Either or is fine with me. More helpful periodic patterns. The noble gas configurations. And thank the Lord for noble gas configurations, because that tungsten one was a long one to write out, wasn't it? Very, very, very long. So because scientists and chemists in particular always like to, cut corners as they can, there is a way of doing a shorthand configuration so you don't have to write the whole thing out. Let's discuss what this means. You're going to use a noble gas to represent your core electrons. Well, what are the core electrons? They're everything but the valence electrons. The valence electrons are the ones in the outer energy level. So we're going to identify the valence electrons, but everything else will be represented by a noble gas for the core electrons. The valence electrons on the next row and the electrons in the next row will fill, okay, according up until the element. And this doesn't really sound or like you're not probably getting a good visual picture of this. So let's actually work a problem and look at the periodic table to do the shorthand configuration. So for example, sulfur. Here is sulfur over here. For example, if I wrote out the normal configuration, I'm going to end up here 3p, 1, 2, 3, 4. I'm going to end on 3p4. So I write it out, 1s2, 2s2, 2p6, 3s2, 3p4. That would be the normal long configuration for sulfur. Well, instead of doing that, This is how you would do the shorthand configuration if you wanted to. You look at sulfur, you go up one row and over here to the noble gas. Up one row, down over to the noble gas. The noble gas for sulfur to represent the core electrons happens to be neon. So if I'm doing the shorthand configuration, I would put neon in brackets like this, like so. Now, neon goes through 2p6, right? This is 2p, that fills 2p6. So really, the neon is representing this part of the configuration. It's shortening it down. I don't have to write all that beginning part out because everything in that is neon. Then all I have to do to get the rest of the configuration is start in the row that sulfur's in and finish filling it out. So I add the 3s2 on, and I add 1, 2, 3, 4, the 3p4. So as you can see, it shortened it down a little bit. I didn't have to write as much. Now, the shorthand doesn't work or isn't much shorter for the elements at the top of the table because they have fewer electrons. But for, say, tungsten, it really does help a lot, because if I wanted to do tungsten shorthand, I would go up here and go down. This would be the noble gas I would use, and I would put xenon in brackets, like so. Then all I had to do is start here for tungsten, the row that tungsten's in. So I would add on my 6s2. I would still have to go down here and do the 4f14. And then I would count 1, 2, 3, 4 into the D block, so 5d4. As you can see, everything that we wrote out for tungsten on the previous slide, this is a much shorter configuration, doing the xenon in brackets and then just adding on the last bit at the end there. Definitely shortens it down for an element like tungsten. So you can use the noble gas configuration unless it says you have to write out the entire complete configuration. So think about that too when you're looking at your problems. So the sulfur one here, I put in the answers for you here, okay? This would be normal sulfur, 3p4, okay? The valence electrons are the ones in the outer energy level. So this is where you look for energy level 1, energy level 2, energy level 3, or these guys right here are the 3s, excuse me. This is 2 and this is 1. So the outer energy levels are the 3 here. If you take these and add them together, 2 plus 4, that gives you 6. So that is why the column that has sulfur, oxygen, and all them, they have 6 valence electrons, is because they have 2 in their S, 4 in their P, so they get a total of 6 valence electrons. So when we said column, 16 has 6 valence electrons, this is why, because they're always going to be S2, P4 elements. So they're going to have a total of 6. Now, if we wanted to write out the shorthand, we would use the neon to represent these core electrons here. And then, of course, we would just tack on those outer electrons past that point. Now it's your turn. Let's try germanium. See if you can write out the noble gas configuration for germanium right here on the periodic table. Okay, so hopefully you were able to go and figure out that you go above germanium and then down to the end to get argon as your noble gas. Then you come over here and start in the row with germanium. So you would fill the 4s2, the 3d10, and then 2 into the 4p. So this would be the noble gas configuration for germanium. Here's another representation or view of it. use the arrow, go up to the row, put in the argon, fill the 4s, 4s2, fill that 3d, 3d10, and then go into the 4p, just like that, just like we did on our periodic table. Now we're running out of time and I do need to go over some of the ion stuff. So if you want to do more practice with noble gas configurations, you can. They're in here, they're in the PowerPoint. You can go through these if you'd like. And the answers are here so you can check your answers, see if you get the correct answer for that. But I want to talk about some ion configurations because you need to know how to do those for the choice board, and we need to make sure you have some information provided about these. There are two types of ions. We have anions and cations. So there's two different methods depending upon which kind of ion you're forming. This is what happens when you have an anion, one where it has gained electrons. It has added electrons. All you have to do is add the electrons to the configuration, keep adding to the configuration. So it's really, not too bad or too difficult. So say we wanted the oxygen ion O-2. Basically, a regular oxygen is going to have 8 electrons because that's its atomic number on the periodic table. So all I have to do is really add 2 electrons to that count. So 8 plus 2, that gives me 10. So all I have to do is add 10 electrons to my configuration. And if you look here, here's oxygen, normal oxygen right here, where it has 8 electrons. If I add in another electron and another electron, now I have 10 electrons and I'm gonna end up looking same configuration as neon. So that's basically all you do is just add the electrons in and you just keep filling where you need to fill extra electrons. So for oxide, O-2, you're just gonna fill it normally, 1s2, 2s2, 2p6 though. For regular oxygen, you would stop at the 4. But because we're adding in 2 electrons, we're going to go all through adding 2 more to end and fill up that 6. That 6 in the 2p. So the anion part is easier because all you do is add. So looking here, comparison, oxygen atom versus oxide here where you have the oxygen ion. You have the 8 electrons versus the 10 electrons. Just add 2 more to your configuration. That's a pretty easy thing to do. The harder part is the cations. They are a little bit different. Cations, remember, are atoms that lose electrons. So they're giving away their electrons. You have to remove electrons from the highest energy level first. Okay, that's where you take them away from. And the highest energy level is being designated by that principal energy level number, the N number. So you're looking for like the 1s2, this number, or if it's like 4d8, that would be this number. The big consonant or coefficient number there is considered the highest energy level number. And that's where you're going to remove from first. So if we're looking at the aluminum ion, Al3+, what does that mean? That means I'm losing 3 electrons. Okay, aluminum has 13, so if I have 3+, that means I've lost 3. Now I have a total of 10. Total of 10 electrons. Well, we already know what 10 electrons looks like because we just did it. It's neon. It's the same thing as neon. But let's look at the periodic table. Aluminum typically would end up here at 3p1, right? But if we take away 3 electrons and we end up with 10 here, we're going to write out the same configuration for neon. That's easy enough. Okay, we just did it. It's 1s2, 2s2, 2p6, right? Not hard. Let's go ahead and compare them and take a look at the regular aluminum atom versus the ion for aluminum. So 13 electrons versus the 10 electrons. You're going to remove the outer energy level here. So aluminum's outer energy level is typically the 3s, the 3s2, the 3p1. That's where it gets 3 valence electrons. But we're going to remove from here. So we're going to take 1 out of the 3p because that's the highest energy level first. We still need to take 2 more out, so then the 3s goes away. So these 2 orbitals now disappear. They are gone. There aren't any electrons occupying them. And you end up with the ion configuration here. That's easy, but when we get into the D block elements, it's a little tricky. Let me show you one of the D block elements. Like manganese, 3+ is a D block element, and it's a little tricky, and it seems backwards. I'm going to tell you that right up, but let's take a look here. So I'm going to do this one, and you can check the others if you want to, and work them to get a little bit better grasp. Here's manganese. Manganese typically has 25 electrons. Now, the thing to think about here, though, is we're not just taking away 3 electrons in the D block, and I'm going to show you why. Regular manganese, if I write out the configuration as 1s2, 2s2, 2p6, 3s2, 3p6, I'm sure you've already figured out this gets very repetitive. 4s2, and then we have 1, 2, 3, 4, 5, so 3d5. Now the key here is to realize you need to look at the outer energy level, or the highest energy level, principal energy level. The highest principal energy level happens to be this 4 here. The 3s are the highest energy level. We have to remove from the highest energy level first. So these 2 in the 4s, they're the first to disappear. Then we also, because we lose 3, we still have to take away 1 from the D block here. So the Mn3+ ends up being 1s2, 2s2, 2p6, 3s2, 3p6, 3d4. The 4s disappears because it's the highest energy level, although it technically fills first because, you know, it's at lower energy, which is the backwards part of the game here. But because that principal energy level is 4, that's the one that gets removed first. Take those 2 out, you take 1 out of the 3d5, so we end up with 3d4. That's how you would do it if you have a D block element. Now the additional practices here if you want to go, and as you can see, I even wrote out some noble gas configurations to make it easier as well. So you could do that to help you as well.